Greetings to all of you. The session is regarding the chemistry intermediate related with the intermediate, which will be fetching for your international entrance or any competitive exams you are aspiring for. India is conducting JEE Advanced. JEE means examination all across India in order to get the admission into IIT and NIT stream, that is the technical domain. And the NEET exam will be conducted for the medical entrance examination. Telangana and Andhra Pradesh government are organizing BTech admissions by conducting MCET examination, that is state level. In addition, government organized exams will be there called a competitive examination. General studies common question paper is available. There you can find general science is the content, where the session what we are conducting is very much helpful for that kind of preparation. Let's enter into our today's session. This is the one regarding the Nobel Prize in the chemistry for the year 2002 was awarded for the development of methods for the identification and structure analysis of biological macromolecules, with one half jointly to John B. Fan and Koichi Tanaka for their development of self-desorption ionization methods for mass spectroscopic analysis of biological macromolecules, and another half to Kurt Wurtz for his development of nuclear magnetic resonance spectroscopy for determining the three-dimensional structure of the biological macromolecules in the solutions. This is the one purely related with the analytical tools. One is related with the mass spectroscopy analysis, and either with the NMR spectroscopy. So the three scientists jointly accorded with the Nobel Prize in the year 2002 in the field of chemistry. Let's go with the brief info regarding the scientists. John B. Fan contributed for this year 2002 Nobel Prize, and Koichi Tanaka also for mass spectroscopic analysis. Kurt Wurtz also contributed for the Nobel Prize in the year 2002 in the field of chemistry because of NMR spectral analysis techniques. Let's go with the brief info. For these scientists, the Royal Swedish Academy of the Sciences has decided to award the Nobel Prize in the chemistry for the year 2002 for the development of methods for the identification and structure analysis of biological macromolecules. Macromolecules are regarded as the complex molecules with the higher molecular weight, either long chains or fibrous in nature, but having long chains bonded with the carbon atoms, especially in the living organisms called biological macromolecules. With one half jointly for John B. Fan, Virginia Commonwealth University, Richmond, United States of America, Koichi Tanaka, Shimadzu Corporation, Kyoto, Japan. They together for what? For their developments of disruption ionization method for mass spectroscopy analysis biological macromolecules, and another half is accorded for the Kurt Wurtz, Swiss Federal Institute of Technology, Zurich, Switzerland, and Scripps Research Institute, Lazola, United States of America. He worked in these institutions, and he contributed for his development of nuclear magnetic resonance NMR spectroscopy for determining three-dimensional structure of the biological macromolecules in the solution. For their work, their eminent focus on these kind of analytical identification and analysis of the compounds, especially biological macromolecules, they are laureated with the Nobel Prize, which is the world recognition. Revolutionary analytical methods for the biomolecules. The year's Nobel Prize in the chemistry concerned powerful analytical method for studying biological macromolecules. For example, proteins. Proteins are the polypeptides which are combined by the amino acids together. Polypeptide chains will be generated. These are the kind of biological macromolecules. The possibility of analyzing proteins in detail has led the increased understanding of process of the life. Researchers can now rapidly and simply reveal that different proteins a sample contains. A sample may composed of various kind of proteins over there. They can also determine three-dimensional pictures showing what protein molecules looks like, and a solution can then understand their functions in the cells. The method have revolutionized the development of new pharmaceuticals. So how they are composed, what will be the chemical skeleton of these protein molecules, and what, how they resemble to look like. All these kind of different kind of new perception got invented and introduced by these scientists. so that a new pharmaceutical auxiliaries are generated because of this kind of perception. Promising application are also being reported in other areas. For example, foodstuffs control and early diagnosis of the cancer and the prostate cancer as well. Because of this kind of identification, even the diagnosis of the cancer type of breeding diseases can be identified. Mass spectroscopy is a very important analytical method used in practical all chemistry laboratories all across the world. Previously, only fairly small molecules could be identified, but John Biffan and Koichi Tanaka have developed the method that makes it possible to analyze biological macromolecules as well, right? So earlier, so mass spectroscopy is available and used as the powerful diagnostic tool for the identification of the unknown organic compounds. But whenever these two scientists made this kind of tool for the application of biological macromolecules, the entire determination, the entire perception to or extend their research in biological organisms got improved, so that this is the kind of unique feature which is located over there. In the method that John B. Fan published in 1988, electrospray ionization, ESI, charged droplets of the protein solution are produced, which are water evaporated. Eventually, freely hovering protein ions remains. Their masses may be determined by setting them in a motion and measuring their time of flight over unknown distance. At the same time, Koichi Tanaka introduced a different technique for causing protein to hover freely, soft laser desorption, right? So they experimented the molecules, macromolecules were taken, and different techniques got introduced into the protein, how they are whole fly, and the soft laser desorption technique is also applied over, and they got analyzed by means of mass spectroscopic technical tool. A laser pulse hits the sample, which is blasted into a small bits so that the molecules are released. Whatever long chain of protein is there, whenever the kind of laser pulse is induced on its surface, so that fragmentation of the molecules got carried and a new tiny molecules got originated. The other half, so this is the way they got fragmentation followed by analysis got carried, and they are recorded with the Nobel Prize for mass spectroscopic analytical tool. And another half is also contributed by the scientist Kurt Hertz, and in their half prize rewarded for the development of another favorite method among the chemists, nuclear magnetic resonance, which is called NMR. This is an acronym for nuclear magnetic resonance. NMR gives the information on the three-dimensional structure and the dynamics of the molecules. Through his work at the beginning of 1980s, Kottwitz has made it possible to use NMR on the proteins. NMR used in the proteins, since the 1980s onwards, he got extended his research. He developed a general method systematically, assigning certain fixed points in the protein molecules, and also principle for determining distances between these. Fixed points of protein molecules got inserted over there, and what is the distance between the protein molecules, so that that kind of skeletal distances are diagnosed. Using the distances, he was able to calculate three-dimensional structure of the protein, how it is originated in the x coordinate, y coordinate, and z coordinate together. That is a three-dimensional picture, and that protein can be picturized on the three-dimensional floor. The advantage of NMR is that protein can be studied in a solution, an environment similar to that of living cell. Okay, so how this protein is surviving, and how it is living, and what is the environment around that entire study got carried by this NMR technical tool. This is the way we got described about the Nobel Prize for the Chemistry 2002 for the development of analytical methods for the identification of biological macromolecules by means of mass and NMR spectroscopic techniques. By this, we can conclude the question number 1 entered into the question number 2, Cambridge Assessment International Education. Toothpaste also contains cinnamol. The structure of the cinnamol is shown over here, and where the six-member ring is there, and the carbon-carbon double bond is over, present over, and here aldehydic moiety is there. If you observe clearly, the entire molecule is existing in a conjugated form. Here, double bond, single bond, double bond, single bond, all double single bonds are in conjugation. It's a perfect example for the conjugated system, alpha, beta, and saturated carbonyl compound as well. Cinnamol is nothing but all denotes according to IUPAC nomenclature, aldehydic species it will be. So this cinnamol is provided. Deduce the formula of the cinnamol to show number of atoms of carbon, hydrogen, and oxygen. Simply, you can go with count of carbons and count of hydrogens and oxygen as well. Before that, let me introduce all the requisite components which were present in the toothpaste, which is very essential for cleansing of our tooth. Abrasive components are required over there, which were composed of 20 to 50%, and water moisture content is required in order to mobilize 20 to 40% it will be. And humectants are required in 20 to 35% composition, and detergents also will be there, where cleansing process were carried 1 to 3%. Thickening agents are there in the minute quantity, 1 to 2% in order to give that kind of thickness. Flavor. So in order to get the good flavor while brushing, so that 0 to 2% flavoring agents are also added over. Sweeteners. So in order to get the good taste while brushing, so that 0 to 2% of sweeteners also added. We can say these are the minute quantities only. Therapeutic agents are also there. Therapeutic agents denotes being mouth is also having various kind of microbes, being it is of long break for this cleansing. So that therapeutics, which are disinfectants, we can say, which are used to kill all the microbes which are present at your mouth, 0 to 2% they are also required. And color preservatives, various colors you can notice in the toothpaste, and preservatives in order to give the longer storage of them. They are also added in the very traces, 0 to 0.05 to 0.5% of these components are required. Among all, one of the component is taken is a organic moiety, where aromatic benzene ring, which is in conjunction with the carbon-carbon double bond and aldehydic moiety, in turn called cinnamol. Everybody aware cinnamol is nothing but cinnamaldehyde. Okay, if you count the carbon atoms, 6 carbons in the benzene ring, and here you can notice 1, 2, 3. So that's C9 system it will be. And hydrogens, if you go with 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens are noticed, and only 1 oxygen, so that need not to mention it's a subscript. So that C9H8O is the entire chemical formula, 9 carbons and 8 hydrogens and 1 oxygen used to address this cinnamaldehyde. So by this, we can conclude the question number 2. Let's move on to question number 3, which is collected from JEE Advanced 2015 question paper 1 question. It is conducted by National Testing Agency. Which of the following is the energy of possible excited state of the hydrogen? Whenever hydrogen is of tiny atom and having only one electron system, that electron wants to excite to the next level. So whenever electron is exciting, what happens? It used to absorb certain amount of energy. In order to absorb the energy, all the energy levels are quantized. Being all the energy levels are quantized, in order to move forward, it needs some external energy. What energy is required from all these given options? Option number 3 is the correct answer. In order to get this one, let me go with the clear explanatory part. Energies in the electron volts per atom are mentioned over for the electrons in the hydrogen atom. In order to excite to the first energy level, you need to give minus 13.6 electron volts of energy. Second energy level, minus 3.4 is required. Third energy level, jumping into third energy level, the requisite amount will be negative 1.51. And fourth energy level, it used to consume minus 0.85 electron volts of energy. And fifth energy level, it is the longest one, minus 0.544 electron volts of energy is required. This is the way jumping or excitation of the electron from one level to another level of hydrogen electron is possible, right? Among all the given options, if you compare, 13.6 is there, but a sign convention got interchanged. If you observe negative 13.6, but they mentioned with positive, entirely reversed, so that you are not supposed to put on. And the next, we are having only option number 3 exactly mapping. For second level of excitation of electron, we require negative 3.4 electron volts per atom of energy. That is given in the option number 3. This is the requisite quantity for the electron excitation for the hydrogen atom. For question number 3, option number 3 is the correct answer. Let's move on with question number 4. JEE Mains 2015 paper 1 question conducted by the National Testing Agency. The intermolecular interactions that are dependent inverse cube of distance between the molecules. Inverse cube of distance between the molecules is nothing but 1 by r cube. So that is given by hydrogen bonding. Let me explain in detail. Dipole-dipole interactions dependent on the inverse cube of distance between the molecules. That dipole-dipole interaction in turn known as a hydrogen bonding. Hydrogen bonding is an example of dipole-dipole interaction. The strength of the interaction depends upon the magnitude of the dipole moment and polar molecule, size of the molecule, charge, and the size of the ion. All these are the dependency factors in order to measure the extent of interactions among the dipole and the dipole, which in turn said to be a hydrogen bond. So that for question number 4, option number 4 will be the correct answer. Move on to question number 5, which is conducted by the Telangana MCET examination in the year 2020. The highest oxidation state observed in the first row transition metal is మొదటి వరుస పరివర్తన మూలకాలలో కనపడే అత్యధిక ఆక్సీకరణ స్థితి. First row of the transition metals, maximum extent of oxidation state to be depicted, that will be a +7. Everybody aware manganese is accompanied by a +7 oxidation state in the first row of the transition metals. And moreover, most common thing for the transition metals are variable oxidation state because of comparable energy between the 4s level and 3d level, so that we are convenient to remove the electrons from d orbital or as well as s orbital, so that whenever electrons, maximum extent of electrons when removed, 5 electrons from the d orbital and 2 electrons from that s orbital, that accomplished with the +7 oxidation. But if you compare the entire transition elements, the maximum oxidation state accompanied by osmium, that is +8. If you go with osmium tetroxide, where we are having 4 oxygens, each oxygen contribute -2, so that osmium is accomplished with the +8. But they are asking for only first row. In that first row, +7 is possible, that is with manganese. So if you observe that entire series of elements in the first row of transition, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc, among all, manganese atomic number is accomplished by 25, and the possible oxidation states are +2, +3, +4, +6, and +7. Up to +7, this is the maximum level over there. Okay, how many electrons you are supposed to remove? 2 electrons from the 4s level and 5 electrons from 3d level to be removed, so that 7 electrons if removed +7 is possible. This is the maximum extent you can notice. And orbital electron arrangement representation is provided with the noble gas notation. Organ accompanied by the 4s electrons are 2, and here 5d electrons are available. If you pick up all these 7 electrons, so that +7 is possible, this manganese is the element which is accompanied by +7 oxidation state over there. For question number 5, option number 2 will be the correct answer. Move on to question number 6, last question of the session, where based on the quantum numbers, what will be the maximum number of elements for the 6th period of the periodic table, right? క్వాంటం సంఖ్యల ఆధారంగా ఆవర్తన పట్టిక 6వ పీరియడ్ లో అత్యధిక సంఖ్యలో ఎన్ని మూలకాలు ఉన్నాయి? ఓకే, so here 6th period of the periodic table, how many elements are there? So in order to go with the expected answer is 32. 22 may not be possible. You can't find 22 anywhere. So 30 may not be possible. 34 is also not possible. Only the requisite number is 32. Let's see how can we explain this. In the periodic table of the elements, the period indicates the value of the principal quantum number. So here Total of 7 periods will be there. 18 groups are there. All the horizontal lines are called periods. Vertical rows are called groups, right? 18 groups will be there and 7 periods are available in the entire periodic table. If you observe that periodic table, each period represent the principal quantum number. N is equal to 2. If you are going to represent only 2 elements, you can notice one is hydrogen, second is helium. So if you are taking second principal quantum number, N is equal to second period will be there, where you can notice lithium, lithium followed by beryllium, boron, boron followed by what? Carbon, nitrogen, oxygen, fluorine, and neon, noble gas. So always every period is ended up with a noble gas over there. So this is the way principal quantum number represents, it's a period number. If you're going with N is equal to 6, they are saying N is equal to 6 period we are going with. So N is equal to 6 if taken, that is the principal quantum number is provided. For that azimuthal quantum number always in -1, right? So N -1, sorry, minus L, 0 plus L values will be there. 0, 1, 2, 3, 4. Okay, 0, 1, 2, 3, 4. So this is the way we can go with according to Auber principle. Auber principle, what Auber principle will say? Auber principle will say that always electrons to be entered into the orbitals according to their increasing energies. We have to fill the orbitals in the increasing level of their energy, which is called Auber principle. The energy of 6d subshell is even higher than the 7s. Okay, so actually in number 6d to be filled, later on 7s we have to move on. But in energy wise, 7s will be least energy, 6d will be a highest energy. So that we have to fill 7s first, later on 6d will be filled. In the 6th period, especially in the 6th period, the possible orbitals will be, one is 6s, one is 4f, one is 5d, one is 6p. These many are there. S orbital, everybody aware, only spherical, one orbital will be there. F orbitals are 7, able to accommodate 14 electrons. D orbitals are 5, able to accommodate 10 electrons. And P orbitals are 3, able to fill up 6 electrons over there. So that let me count: 1 for S orbital, 7 for F orbital, and D orbital contributing 5 orbitals, and P orbitals are 3. So that 1 plus 7, 8, 8 plus 5, 13, 13 plus 3, 16. So the total possible possible orbitals for 6th period will be 16 orbitals will be there. If 16 orbitals are present, each orbital will fill up 2 electrons maximum. So that maximum capacity to fill are 32 electrons. 32 electrons if filled up, 32 elements are possible obviously. So that the possible elements in the 6th period will be 32 elements. This is the way we can go with the calculation. How can we fill the period, or else how can we fill the group as well? So this is the way we gone with the entire session, which is covered with the various dimensions of chemistry, and we gone through organic chemistry, inorganic chemistry, physical chemistry, general chemistry. Most of the corners, most of the important points got covered over, and all the information, whatever we procured over here, is collected from the most authentic websites, and the data is most informative in nature indeed. So I'm requesting all to like the channel, and in order to comment, we have a question for the session. In order to comment, the question is, what are the various kind of principles we need to follow in order to fill the electrons into the orbitals? There are certain kind of definitions we have. Auber principle will be there, and either is said to be Hund's rule, and either is a Pauli's exclusion principle. These are most fundamental in order to fill up the electrons into the orbitals. So you can mention all the definitions of these 3 principles whichever required to fill the orbitals, and that can be posted in the comment box for the session, and share with the aspirants who are more serious about the examinations, and subscribe this channel. Definitely we will go with the new content in the near future by your support and encouragement. Thank you. Thank you one and all.